Thank you very much. So first of all, of course, thanking the opportunity to, the invitation to be here today, and of course, congratulations on the anniversary. So after listening to the previous talk this afternoon, I think that it's important also to acknowledge the role of the studium, because as you said, sometimes it's hard when we speak with people which does not work in our same discipline, and I think that even like events like today, so we can see that what other people is doing in fields which is outside from our expertise, but somehow everything is making us to do something more to give us another vision. And because unlike Da Vinci, we have a tendency right now to be too focused, too specialized. So maybe we should step out of our expertise more often, and I think that is something, a role that you are playing very good, so congrats again. So today I am going to speak to you about water treatment and with some kind of materials, porous carbon materials that we prepare in our team. These materials have been synthesized and prepared for many years in the team, also in collaboration with other researchers that came to the team with a student fellowship. But I will focus on a different application today, which is water treatment. So I got inspired also yesterday by the first keynote speaker, as I guess everybody else. And I decided just to show you again this beautiful picture of our planet. I am sure that you all remember from your elementary or even before high school that we all learned that this blue color is what makes the Earth fantastic for us to live in that. And also we are familiar with this idea that there is plenty of water on Earth, and because it's covered the surface by 3/4 are water. Well, this is actually the wrong idea that we were told when we were little, and as long as you are growing, you realize that the situation, and particularly when you work in this topic, the situation is not really that fantastic. This is the situation, also an image that we saw yesterday, because this is the amount of water that is available for of fresh water that can be directly used and that can be used. And this tiny spot in here is the amount of water that we can use directly without any processing, either for potabilization or just after use. So, and this is of course a problem because, and this has been recognized by the United Nations, so because there is a lot of people that does not have access to water, and we'll speak about clean water or not. And also because it's becoming also a politics problem. There is this film that started out in 2008, and you can see the trailer if you want in this link, where they, some years ago, they were starting also to speak about that water, of course, is becoming a big issue, and it's becoming a core of it's being called the world water wars. Some people already speaks about the water cartels as in analogy to drugs, also because of the power and for the privatization of water, which is a real risk to the humanity. So that's something that we have to take into account. And also because it's not only the availability of water, but also what we do with it. Unfortunately, well, this may be a very theatrical sketch of water, but it's actually the reality of when humans are getting to the picture. This is what we do. We pollute water very much, so we have to deal with this kind of pollution. So we were also familiar with this idea of that water is a renewable resource. So, but is it? I don't think it is. It may be, but it's not. We have to do something. We just cannot use water and then discharge it to the environment, because it has much more implications than we think. This is also why the United Nations, they have considered this sustainable development goal to provide clean water and sanitation to everybody. And the reason for this is not only the big objects that you can see in here, it's because of all the activities that we develop in our daily life. So, of course, when we speak about pollution, we immediately think about the big sectors like industry or agriculture. So, of course, they do pollute because they use a large share of the water, but we also have to look at the domestic uses and in our society, and this is where I will focus my presentation. So, just to give you an example of which are the common pollutants that we can find nowadays in the water. This is, again, perhaps an exaggerated image, but it's just to draw your attention on that the drug portal to the world is actually the consumption of many products in our daily life. And also there is, it's not only the chemicals that we use, in this case is the pharmaceuticals, but also the development of some viruses. I'm putting here an example about COVID, because ever since we had the first lockdown, we were invited by the European Union to shift some of the activities of our projects to look into the water to see what happened in there. And the good news is that COVID is not as resistant as many other bacteria, so it does not have a tendency to proliferate in the water pipes, and the wastewater treatment plants are usually or typically a natural barrier, so that it does not go and infect once we have the usual treatment of water. Unfortunately, this is not the case for many other bacteria or viruses, and this is why we have to look into more advanced treatments to depollute water. Just the last example is that public awareness is also very important to realize that the first studies were carried out, I think, in the US. You can find here some of the studies published in the EPA webpage. In 2005, in drinking water, they found extremely large amount of pollutants that they belong to the family of pharmaceutical compounds, pesticides, and so forth. So you may even recognize some of the names in here. And another example is in 2011, and a study that we carried out in collaboration with the University of Oviedo, where we analyzed two different, in the city of Oviedo, we analyzed two different places for contamination. It was the water outside the main hospital, where we can see some of these compounds, paracetamol, ibuprofen, naproxen, and you can have here the concentrations, which is in ppbs. And then we also analyzed that in the inlet of the wastewater treatment plant, which is 20 kilometers far from the hospital. And it was very surprising to see that some of these compounds even increase the concentration. So the hospital is not the main contributor to the water pollution, is our activity. Because when we take these drugs that we need, actually we take a dose which is much higher than the one that we process. So it is just gets to the water due to the human excreta. So you can see that the concentration is really important. And something more recent, this is a mapping of our region, Région Centre, and this was published in 2021, last year, about the pollution of the groundwater in this case, with mainly due to pesticides, because there is of the large agricultural activity that we have in this region. So with all this in mind, I think I have convinced you that we have to improve the methods for cleaning water, otherwise we would be in a very high danger. In our case, what we do is we treat the water with these materials, carbons, porous carbons, and we do adsorption treatments, and also some coupled with some other advanced oxidation treatments. So I'd like to draw your attention to this word. So we do adsorption with a D, which is not the same as absorption with a B. And I think this is also very representative of what's the difference. What we do is we use materials which have a porosity at a nanometric scale, which means that we have just a few nanometers with a very high internal surface area in a three-dimensional structure, so that these pores of nanometric scale, they have a tendency to accumulate different molecules. And this is the beauty of the adsorption process, that they accumulate almost any molecule, so it's non-selective, meaning that when we have to regenerate, or if we want to, we can easily reverse the process, because there is no strong bonding between the molecule which is retaining the porosity and the adsorbent. Also, we used different carbon adsorbents. It's a pity that it's too dark. You cannot see. These are just images of different morphology of the carbons. And just for you to have an idea, carbon materials are well known for many years, and the synthesis of nanoporous carbons is actually based on a patent that dates from the 1900s. It's a pattern that everybody else is using nowadays. Of course, there is a lot of research also on modifying, trying to find new precursors or modifying to control some selectivity. But in the case of water treatment, we use the carbons following the common procedure. And as you can see here, there is a lot of applications. Liquid phase is one of the highest applications for these materials. And it represents over a $40 billion market, which is very high. So what do we want to do? Because of this non-selectivity of these materials, that they can take up anything, which is an advantage, also we can think that, of course, we can remove any pollutant that is in the water. However, the question is it worth the benefit? Because we need to put more energy or more material, within the end is a higher cost. So the question that we have to answer is it really worth the benefit, worth the impact? Also, is it working when we have these new pollutants which are present in the water at a very low concentration? And also, how is the behavior of the technologies that we develop or the materials when we move to a real case? When we get outside the lab, and other than in our class, we try to deal with the quality of the water. And so are the questions that I'd like to show you our research trying to answer to all these questions. So, first of all, of course, we have to develop some lab scale optimization of the materials. So this is just a global overview for you to see different carbon materials in this case and how they behave to absorb or to retain, which is the uptake of different pollutants. Some of them mentioned before, so caffeine, penicillin, amoxicillins, ibuprofen, and so forth. So what's important in here is that you can see that if we look at one singular carbon, like this one, the adsorption capacity really depends on the molecule that we want to target. So some of them are going to get retained very heavily, which is good news because we will need less material, but others, the adsorption capacity is very low, and those are more prone to get discharged again in the water pipes. Another important thing is that if we look at different carbons like these two, and let's focus only on the ibuprofen, in this case, the orange, the adsorption capacity, it also depends somehow in the characteristic of the carbon. So this is why we have to perform all that optimization of the composition, of the surface, and so forth, in order to understand which are the mechanisms that are giving us the final uptake before we go to a higher scale. Another example is that we may also have what is called the reactive adsorption, and that's something very common in the penicillin-derived pollutants, because as you know, penicillin degrades over time in acidic media, so we have this pattern of self-degradation. This is the reason why we have to suffer these unpleasant shots of penicillin instead of taking them orally, because they will decompose at the pH of the stomach. So if we control the composition of the carbons, we can also control the degradation of these compound of penicillin inside the porosity of the carbon. Why is this important? Because if we have competition in the adsorption capacity of different molecules, if the penicillin is degraded in another compounds which do not have therapeutic activities, we might be releasing something else to the water discharge, but at the same time, at least we are removing the activity, which might be the activity of the initial compound. Also, we have, of course, to study the adsorption capacity of the other compounds in order to see if they are dissolved or not, or if they can also be trapped in the same material. We are also working on developing advanced methods. Why advanced methods? Because with the adsorption, what we are doing is some kind of pre-concentration. So we have the pollutant, which is no longer in water. That's very useful. But at the same time, we have it inside the pores. So we have to do something with the carbon. Either we regenerate it, or we dump it in an landfill, and then it's treated like a very toxic and dangerous waste. So there is a lot of research doing the combination of these adsorption with other methods. One of them is electrophoton, which is using them, the materials in an electrode so that we can apply some low voltage and we can generate radical species in situ. So we have hydroxyl groups, superoxide that interact with the pollutant, and then we have this adsorption, pre-concentration in the pores, but we also have the degradation, which is better, and we have the self-regeneration of the carbon. This is just an example of the conversion with 3 different carbons, where you can see with a paraben compound, where we follow the evolution over time. You see that depending on the characteristics of the carbon, we can have a really very different performance, and not only in the final conversion, but also in the kinetics, which is very important because in the end, most of these processes are going to be in a column of adsorption. So kinetics are important. We also have a different speciation of the degradation compounds. So the idea is to optimize that kind of reactions. We have also done some tests with real water, which have not only the pollutant that we are targeting, but also some salinity and natural organic matter that are all the time interfering with the performance of these materials. So another advanced process that we do is we couple light and then we perform some photocatalysis with this type of material. So the principle is the same. We have the pre-concentration in the pores, and then we apply light to promote the degradation. So these are the type of the reactors that we use. And we have, again, these conversions that you have seen in here over time, and depending on the material, which is not important for this topic today, we can have a faster conversion if we modify the composition or of the material. What's interesting also is that we have to have a look not only at the degradation of the pollutant itself, but also what happens if we don't have a full degradation. If we have some other intermediates in water, we need to know if that is more toxic to the water or not, and so for that we use the standard toxicity methods and based on the luminescence of bacteria, and we can see that when we incorporate our carbon materials, we have a much better response because we are able to degrade these pollutants. One interesting application of that, of course, is that we want to use the natural sunlight in order to promote these advanced oxidation processes. And for this, we have worked in collaboration with a laboratory in Chile, and we have done a few campaigns between 2017 and 19. In the 20, you can imagine why the campaigns were canceled. And we were there using these kind of reactors that they have, because also Chile is one of the places in the world with the highest irradiation. So we were exposing our catalyst to these kind of hard conditions in summer and in winter, because the irradiation is not the same, and we also compare them with the performance in the lab. The important in here is that when we are doing the experiments in the lab, we have a constant flow of photons, which might be, as we've demonstrated, it is not all the time beneficial for the performance of the material. When you have outdoor conditions, even if it's summer, and even if you are in a place which has a very high flux of photon as Chile, we have this kind of parabolic behavior, depending, because you have the beginning of the day and then at the end of the day, so you have cycles like that, and that is actually helping to the material to perform longer over time, which is a very good thing to preserve to increase the lifetime. So these are some of the reactions or the conversions that we got in summer and in winter campaigns. You can see, of course, that there is a big difference. But anyways, if you just have to put your reactor outside, and in winter, you just need to accumulate the treatment for a longer time in order to get the same conversion. So the interesting thing is that in winter, we don't have zero conversion. It's also quite important. What we are doing right now is, of course, so what happens, so is this treatment can be translated to some other places in the planet where we don't have so much sun as in Chile or in Mexico. So this is something that we are doing right now. This is the question is this possible in Orleans? I think it is, and this is something that we will demonstrate hopefully in the upcoming months. Here you have the irradiation of Orleans according to in 2019. This is the average, it does not change. And what we have observed is that even though these numbers in winter are much smaller than those that we have in other places of the Earth, our limit for the irradiation that needed the catalyst in order to be active is actually 0.2. And as you can see, we are above, even if we move in January or in February. So we'll need perhaps to perform our experiments for a long time, but we are able, or we should be able to get some degradation. Well, this is just the biggest CPC reactor that arrived to our lab last Friday. So I just opened the box for you to see, and it has been funded also by the region CEMHTI in the project CONEX, and we are willing to start the experiments this summer. I think the PhD student is not as happy as myself because that means that she will not be able to take vacations in summer, but anyway, we'll manage off-season. So, now some examples. Once we have optimized all these lab scale, even though the last part that I've shown you is not actually lab scale, it's a little bit higher because we can recirculate 50 liters in this kind of a reactor. I will show you also some case studies in bench or real pilot scales. The first one is the application of different carbon materials and different conditions of adsorption in a wastewater treatment plant. This is a collaboration that we carried out with the university and a wastewater treatment plant in Germany some years ago. And the advantage of that is that they had already 4 different prototypes on site. You can have in here the scale, so the dimensions is 6 million cubic meter per year, and so it's really very big, the installations. And what we have is the typical secondary treatment, which is composed of the biological reactor. And the idea, because all these processes are after, they're called the tertiary treatment because they're after the biological reactor. So the idea is to compare the carbons in different configurations after the biological reactor, which is where these pharmaceutical compounds that I showed you at the beginning, they are detected. So the bacteria in these tanks, they're not able to degrade it, so they are, in some cases, the concentration doesn't even change. So in here we have different configurations with granular activated carbon columns, also membrane filters, in this case with powder carbon in order to favor the filtration, also with some membrane reactors, so where the carbon is in contact also with some bacteria. We also have some ozonation and some flocculation system with different configurations. In this case, we were targeting these 2 compounds, an analgesic and an antidepressant, because they were the main pollutants that were detected outside at the outlet or the wastewater treatment plant, and some others that I cannot disclose. And this is what we got. So if these are the 4 different configurations that I've mentioned before, and this is the treatment without the carbon. So you can see that the efficiency, this is efficiency of removal of these compounds is actually very low for all of them when we don't couple this tertiary treatment. So we do need to improve this efficiency. And this is the performance of the different configuration, in this case with the powder, with the membranes, or the granular activated carbon filters. And you see that in the best of the cases, we can reach 90%, which is already very, very good. Don't remember that these are in a very low concentrations of the order of ppts or ppbs, so the analytical effort to detect that is also very hard. So, and even if we are not able yet to remove them completely, at least at an affordable cost, because that's important, the concentration is really very low. So if we remove 90%, we are out of the detection limits for these compounds in most of the cases. Of course, there is a lot of work to carry out in for some other important parameters like the salinity, depending on where the water is coming from, where the wastewater treatment plant is located, and also some the nature of the organic matter, which may decrease increase the efficiency of these materials. So another case study was what would we do with the carbons after when they are saturated? We have to treat them, and this is a big issue because actually it represents 90% of the cost of the technology, and it's really very high. So this is an example of some pharmaceutical compounds in here where we have, in this case, we have performed a simple thermal analysis of the carbon after saturation, and these peaks that you see in here, they correspond to the different loadings of the compounds. So these kind of experiments, we can choose the temperature at which we can do the regeneration, because it's usually a thermal regeneration. So that is, if we have the either desorption and we can recover the compound, which is mostly not the case, but if these compounds are degrading inside the carbon, they usually become also some organic or carbon-based material. So it is okay for the performance of the carbon. So we have selected very mild temperatures in order to save some energy, and this is also, well, some of the characteristics of the carbon after how the porosity is evolving. We see that after a few cycles, we have 4 cycles in here, we have some clogging of the porosity, but still the adsorption capacity is pretty decent, so at least we can reuse them. This is the efficiency of the regeneration. And the thing that we are trying to do now is to induce this photochemical regeneration, because if you remember, with the light, we can also generate, in the presence of water, some radical species. So those radical species will interact with these compounds at a room temperature, so that if we can use also the natural sunlight to do that, we will be saving a lot of energy while contributing to depollute the water. So this is what we have for in comparison with the thermal classical regeneration, and this is something that we are now working also with a manufacturer of activated carbons from the region, and we are also trying to optimize this kind of exposure for different hours. You see that the time is very high because, of course, the energy is not the same, but also we can play with the loading of the carbon in the suspensions of water. This is also something that we are developing at a much larger scale in a European project that is running until the end of this year. So in this case, our contribution is to couple these carbons with light in order to regenerate the carbons, and we are installing this technology in 2 different demo sites. One is a wastewater treatment plant in Spain, the other is an aquaculture center in Israel. So you can easily imagine that the quality of the water that we have to treat is completely different. In here we have a lot of high organic content, because it's an agricultural area, and also we have a lot of pesticides. And in this case, the organic matter is much lower, but the salinity, it's aquaculture, so the salinity is very, very high, and that is actually hindering the performance of the carbons. So the idea in this case, this is a picture of the wastewater treatment plant. This is the biological reactor, and this is where we have actually installed our device. This is a picture of it, and just some connection, and is receiving the water after this treatment. And we are also coupling this with some UV lights based on LED technology in order to be able to work on the degradation overnight when there is no natural light. The idea is to assure that all the pollutants are degraded, which are not a very high concentration after the secondary biological treatment, but anyway, and to do the regeneration of the adsorbent on site, so that they are not obliged to ship the expent carbon material to the manufacturer of carbons. And in the case of the Israel, we want to use that configuration as a means of water disinfection units, and also to promote the degradation of the organic matter, which in this case is easy because it's much smaller, and also to do the on-site to extend the lifetime of these carbons. So I'm almost done, so I will skip this, and perhaps I will give some time for the questions. So my concluding remarks is that it is our responsibility to look after the water we have, so we have to try to leave it in the better condition that it was after our use, because it's not only because it's scarce and it's a precious resource and then we need it, it's also because the impact on human health, but also on the ecosystem can be really dramatic. So thank you for your attention.